Hello class and welcome to ENES 101, Introduction to Engineering. Sorry to get off to a snowy start, but hopefully you're having fun in the snow today and even possibly tomorrow, but we'll see what the university has to say. Goodness. So we're really excited to start the class this year. We've got a new project that we implemented last fall. We're bringing that back for the spring, and it's really just going to be an exciting time for us and an exciting time for you guys as well. There's a lot of new stuff you're going to learn this semester, and we're really excited to have you here and have you get started on your path toward being an engineer. So my name is Dr. Von Lockett. I'm the guy in the middle. I teach in the mechanical engineering department here, and I've been here for a few years, but I've taught the introduction to design before many times. We also have Dr. LaBerge, who's from computer science and electrical engineering. He has taught this class at UMBC even more than I have. And we have Dr. Rowe from chemical, biological, and environmental engineering, who's on board from that side of the house this time around. His focus is in entrepreneurship, and hopefully he'll bring some of that interest to you in lectures today. So what we're going to talk about today is sort of what it means to be an engineer, what engineers kind of do, but most importantly, what we hope you get out of this class is how engineers think, because it's how engineers think that separate us from other professions. Alrighty, so without further ado, let's get started. Some might call this an existential question, but to be honest, those in the National Academy of Sciences, the National Science Foundation, and organizations that study how people get into engineering programs, how people get into engineering jobs, and more importantly, how they stay in engineering jobs, their focus is on this question exactly. Do you know why you're here trying to get an engineering degree? So sit and think about that for a little bit, and I'll give you some time. Alrighty. So your answer to that question can fall in a lot of lines. Sometimes it's because some family member actually told you engineering's a great job, engineering's a great profession. You thought about it for yourself and you looked into it and you went into it. Sometimes your family pressures you into STEM jobs, science, technology, engineering, and math, and engineering becomes the one that bubbles to the top. And it's kind of your decision, but it's kind of theirs. Sometimes it's just for the money, because engineers have relatively stable employment and can have pretty good incomes. And sometimes it's because you just like to tinker on things, solve problems, or generate solutions to anything and everything that's out there. And all of these have different impacts on how you'll actually enjoy this profession in the future as you go forward. Because the people who research this have found that the folks who have the least satisfaction with their degree and the least satisfaction with their job are the people who got into it solely for the money. And the reasons for that are because you can actually make more money in other professions. And if you ask around in some of your friends in other majors, you may find that you can make more money in other professions with an easier career path in college. Less homework, less late nights, less projects. But often that's not why we get into engineering. Sometimes it's because we had exposure to it from our families. Family pressure is a reason that people get into engineering, but that too, in the long term, can turn into a situation where you're not as happy with your job as you might be otherwise. Or if you're just exposed to it and you find that you like it for yourself, or if you found engineering to be an interesting thing because you like working on problems and solving things. Those are the two highest categories for people who eventually have satisfaction in their jobs, satisfaction with their degrees, satisfaction throughout school. So take some deep thought and give yourself some time to think through that. Why are you here? And make sure that you understand what your purpose is. Because if you know why you're here, you have a better chance of getting out of this experience everything that you need to. I can tell you exactly why I'm here. I'm here because of this Tacoma Narrows Bridge video, which I saw probably when I was about 2 years younger than you in an engineering camp in Houston, Texas, University of Houston. And what I saw was a steel suspension bridge waving in the wind like a ribbon. And I thought, that's not possible. But it was, and it happened. And I thought to myself, wow, that is the coolest thing I've seen in real life up to that point. And in real life, meaning it was a video. I wasn't there, but not CGI, not computer animation. That really happened. And for me, that was the spark that drove me into mechanical engineering. It drove me into solid mechanics. It drove me into studying materials and deformations. And so I thought that was just cool. And that was my spark. So the question becomes, what's yours? And if you want, you can copy the link in the bottom right and take a look at this video. If you've never seen Tacoma Narrows, it is a cool thing. Well, if you got into engineering to get a job, get a good job, and get a good salary, then you're kind of in the right place. Engineers typically have good employment. It follows the GDP of the country, which is how much the country produces on average every year. And electrical engineering, as you can see, has the highest. Mechanical engineering, chemical engineering come in about the same. Biomedical engineering is kind of down near the bottom on this particular scale, but in general, engineering ranks pretty high up there with respect to other professions and even other college professions. Also, the employment is fairly consistent. So engineering is a good place to be if you're here for a job. Now, you can also find lots of places that give you information on the labor market outcomes of college graduates by major. What is this? This is essentially how often do they get jobs? What do those jobs look like in terms of salary? And here we can see what do those salaries look like when they get to mid-career. So how do those salaries increase? And again, we have computer science, computer engineering at the top. Now, chemical and electrical have sort of surpassed mechanical engineering, but not so by much. Mechanical engineering is sort of still on the board if you look at the median wage mid-career. So again, if you're here for stable employment, if you're here for a pretty good income, this is a good place to be. Now, with the job market as it is, with the economy as it is, I would strongly suggest you guys keep an eye on these numbers. You can find them at the newyorkfed.org at the bottom. You can also find them on the Bureau of Labor Statistics, BLS. There's a thing called the BLS handbook that comes out of the federal government as well, which tracks all of this information as well. To also help you on the back end, try and get into research, internships, working in labs on campus, student organizations where you can show some product that you've done so that when you get to the end of your 4-year degree, not only have you taken classes, you can sit in an interview and tell somebody outside of the class, here is what I did. And that's really going to be the selling point. Because with engineering degrees across the country, there's an accreditation organization called ABET, Accreditation Board for Engineering and Technology. They ensure that all degrees have to be the same thing. So that piece of paper that lists all your courses is going to be pretty much reviewed the same way as everybody else's in terms of what you have learned in class, I guess relative to your GPA. But you take the same things in class. So what you do out of class can actually show some distinction. And if we get back to one of those big existential questions, why engineering? One of the reasons that people get into engineering is because, like I said, they're natural problem solvers. But what problems are out there for us to solve? We've got existential problems with the climate. If you've looked into healthcare for your parents, or if you know about your grandparents, you know the issues there. For costs, people are living longer. As they live longer and they age, we have more health concerns to deal with. We have space exploration, not just for SpaceX, but in terms of low orbiting satellites. If we want to go farther to find resources, all of these things are large problems that need to be solved, and they're going to be solved by engineers. If you're someone who likes to build new things, engineers are innovators. We design new technologies for tomorrow. 10 years ago, you would not have, 10 years ago, I would have not have thought I would have seen so many electric vehicles on the road as I do today. But when I drive around, I see Teslas all over the place. Why is that? Because electric vehicles have made this huge leap in the past 10 to 15 years. So now they're becoming much more commonplace than they were before. I'll tell you this, it kind of shows my age. When I was in your position, yes, there were no cell phones that could fit in a pocket. We had these cell phones that you would carry around in a briefcase. They were about the size of large walkie-talkies, and that was the state of the art. But right then, we had actually not an exact, but we had one of the engineers who came over from one of the telephone companies that actually makes cell phones, and it was Motorola. And he showed us this little flip phone. It looked like a communicator on Star Trek that you just flip open and you talk in. And he said, this is what's going to be the next best thing in about 2 years. And lo and behold, it was. And then years after that, you can see what happens. Everybody's got a cell phone. Back then, that was the technology of tomorrow. So we ask ourselves now, what's the new technology for tomorrow? And engineers can also be leaders. They're leaders because we teach you a way to solve problems. It's a process, a way of thinking that allows you to take those skills into business, into research, into entrepreneurship, and move pretty much anything forward with a structured process for problem solving. So your engineering journey. You may be familiar with snakes and ladders or even chutes and ladders. If you played one of these games when you were a kid, maybe you did, maybe you didn't. But the goal is to get from one side of the board to the other side of the board, rolling dice, moving a piece. But the point is that we have, as you can see, some ups and downs all over the place. So maybe you got into engineering because you like to build and you like to create things. But once we build and create things, engineers, we have to test them. We have to see how well they work. We should expect failure because nothing's going to work perfectly the first time. But then we learn from those failures and we iterate. We redesign, we rebuild, and then eventually we reach our point of success. The thing we've built actually solves all of our problems. We have this up and down and this back and forth. But one thing we can't forget, even as engineers, we sometimes think it's that lone wolf who goes out and solves problems, but today's problems are so complex that we actually have to do them in collaboration with other people. So one of the things we'll learn about in this class is teamwork. You'll have a good percent of your grade worked out with the rest of your team, the projects you're working on, the presentations you'll give. You'll learn to work with others, the highs and the lows of it, but it's all engaged in trying to get you to be an engineer and have an experience that engineers would have prior to getting on the job and the exposure to what can happen when you're actually there on the job. So what is engineering design? Well, engineers use science and math to solve technical problems to the satisfaction of an end user. What does that mean? Well, we can bring in aspects and knowledge from biology, from computing, from physics, from chemistry, from mathematics, all put into finding the solution for some of the world's biggest problems, or even some of the world's smallest problems. But we generate these solutions using all the knowledge that we have about the physical world, all the things that you're learning in the classes that you'll be taking over the next few years. And those solutions to problems usually turn out to be something of a designed nature. On the right, we see a typical solution for a mechanical engineering problem where we have concept designs, we have sketches, we realize these things and bring them into the real world. Now, they may not actually be physical processes, physical items that are produced. Mechanical engineers generally produce physical things. Chemical engineers may produce a process that creates a new compound or takes existing compounds and turns them into something we need in a new way. For computing, it could be code. The AI explosion is an example of this as well. Physics and physicists, if you look at the study of solid state physics and looking at people trying to go after cold fusion, that was a big thing when I was in your age, but physicists are trying to understand the world, and some of their new understandings have really pushed forward technology. If you can think about all that goes on in a cell phone and how some of it is really based on things such as electron tunneling, which is a really weird concept. If you're interested in that, you should Google it. But the physicists have actually brought us really huge endeavors in science that have made their way into the technologies that we use every day. Similarly with biology. I remember when the COVID pandemic was out and we did not have a vaccine, but biologists working in the pharmaceutical industry came up with a vaccine to solve that particular problem. So engineers across the scope solve problems. So engineering design, it's been around forever. Here we're showing Roman aqueducts from 312 BC. We can actually find older examples of engineering, but this is one that is pretty much ubiquitous. Everybody knows about it. We take water from a reservoir, we run it down a hill through a conduit, and when we have to span large spaces, what do? We raise it above the ground, but at a slight angle. So it's sometimes this engineering is functional, but sometimes it's aspirational. If you look at this quote from John F. Kennedy, we choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Engineers often tackle the most difficult problems. And in 1962, we were faced with the space race against the Soviet Union, and the engineers in the US decided we will make this happen, and they did. So we were reaching for a goal that at the time people thought might be impossible, but we did it. At times engineering is fearsome. Here's a picture of the US Navy's railgun around 2010, 2012, 13. This thing fires a projectile, a sabot shell, a slug of metal. It's 23 pounds at 5,300 or so miles per hour, Mach 7, if you can believe that. These projectiles cost about $23,000 versus a $500,000 to $1.5 million conventional missile that was being used by the Navy at the same time. These things have a 100-mile range, and if you think about it, what's the kinetic energy of a body? 1/2 mv squared. This thing is moving at 5,300 miles per hour. The stories around these things were crazy when they first came out. One of the most interesting ones I heard was that the Navy set up this huge bunker, 10 by 10 by 10 foot reinforced concrete. They instrumented it with sensors so they could tell what the impacts were, what happened to this thing when it was struck. They fired up the railgun, they slammed it into this 10 by 10 by 10 concrete bunker, and all that was left was dust. They had not expected that at all. Completely obliterated the target. They couldn't collect any data because there was nothing left. Engineers built that. And if you want to see this thing in action, you can go to the PowerPoint slides that are also posted separate from this video and click on this slide in the viewer option for the slideshow, and it'll take you directly to it. And you'll see it cuts through these steel plates like butter. Sometimes engineering is humbling. I remember when I was, more than a few years in front of your position, a few years after your position. I was in graduate school working on a PhD, and there was this thing called the traveling salesman problem that I looked at, which was essentially if you have a salesperson that has to go across the country, they have to hit every state or the capitals in every state. What's the shortest path to actually do that? Or if they have a certain number of cities that they want to hit across the country, what's the shortest path to do that? And then you can put constraints on it, such as they can only cross rivers one time, or they can't backtrack across their own path, it can't intersect. But essentially, this problem at the time was considered intractable, NP hard, if you understand the computer science for it. That was then, and within the span of 3 or 4 years, we had mapping programs. You could actually pull up on your phone, on your web, a map that would take you from point A to point B, calculate the routes, give you the shortest one. in the span of 3 or 4 years. That was a transition from something that was considered impossible to something that you could do on your phone. That always gets me because I was there working on these problems during that transition. Engineering is sometimes playful. We all know drones. We've probably seen even now even more of these toy drones where someone decided, hey, I love Star Wars. Can I turn this into a toy for kids? So they made a Star Wars themed drone. Here we can see the stormtrooper riding as well. Engineers make everything from weapons to things that are playful. And sometimes they make things that are elegant, if not supremely beautiful. Here's an SR-71 Blackbird built around 1964. Maximum speed of Mach 3.2. Can run at an elevation of 80,000 feet. And this was built again during the Cold War specifically to solve the problem of dealing with Russian interceptors and Russian missile systems. We'd had a plane shot down in the US on a reconnaissance mission, and the US government decided we need to build something that cannot be shot down. The specifications weren't initially how fast can it go, how high can it fly. The specifications were we cannot have another plane shot down. So engineers took up that challenge and built something that could fly so fast and fly so high that it couldn't be caught by enemy missile systems of the time or caught by enemy aircraft at the time. They took up the challenge and went forward with this and made it happen. Now, if you have the chance to get down to the new Air and Space Museum and see this in person, one of the samples of this airplane is there, and it really is this cool to see. And if you know X-Men lore, then you might actually recognize this as well. Sometimes engineers have the ability to create something of beauty and minimal complexity that actually improves the world. So here is an example of a child warmer, because in many places around the country, childs die for reasons that can be solved. Each year, more than 1 million babies die on their birthday, and 98% of these deaths occur in the developing world. The leading cause of these deaths were preventable and treatable complications, and one of them had to do with hyperthermia in premature babies or babies that had some other type of health-related or distress problems. So a company called Embrace came up with the idea of, can we make a material that changes phase slowly over time, and that phase change releases energy and allows a baby to remain warm at their body temperature. So it's something that you transition to one phase throughout the day, and then overnight, when temperatures go down, you put the baby in it. And for hours, that baby is kept warm based on the phase change in the materials that were developed by chemical engineers. So 750 million people as of 2025 globally had no access to electricity, and millions more had an unreliable supply. So a company called Gravity Light came up with an invention built on another innovation, LEDs, to produce light in these environments where there's little to no electricity. Well, how do we do this? Well, we use gravity. So we have an LED, very low energy source that can generate photons, light that we can see from. We have a bag hook where you can have a bag that holds anything as simple as rocks and dirt. Those things pull down due to gravity if we hang the light up from some point. And inside here we have a pulley and gears which actually rotate a generator, and that generator generates the small amount of electricity we need to power this LED, and that LED then gives us light. All these systems together work to solve a problem that was widespread, as I said, 750 million people as of 2025 globally. Alrighty, this is what engineers do. We bring solutions to the world, we solve big problems, we take up challenges, and we use physics, mathematics, computer science, biology, and mechanical engineering to actually solve these problems. So what do engineers do? What will you do as an engineer? Well, you'll apply math and science. Because engineers, you take a lot of math, and we're also scientists because we understand how the world works. We design solutions because we're problem solvers. We manage projects, which is actually a big part of what engineers do, because you need these rudimentary project management skills to get from A to B with a lot of moving parts, which is something we'll give you exposure to in this class. And we'll give you a little bit of project management training and how to do that. And what do we do from there? We try and change the world.